Hello class, welcome to the final segment in lecture 25. And in this segment, we're going to talk a little bit about some of the chemical properties of the atmospheric pollutants that we introduced in a previous segment and talk about why, and with that, we'll sort of talk about why we care about the concentration levels of these various compounds in the atmosphere so much. So we'll go ahead and start things off by first looking at tropospheric ozone. And we'll sort of see why this is the case a little bit later on when we talk about nitrogen oxides, but tropospheric ozone typically forms in response to high levels of ultraviolet radiation that reach the troposphere. And there's a chemical reaction, there's a chemical reaction that takes place to produce that, and again, we'll take a look at that a little bit later on. But if you have high levels of tropospheric ozone and you start breathing in that ozone, that molecular ozone, then you can start experiencing some adverse health effects, primarily concentrated in the respiratory system. So usually that's in the form of inhibited lung function. Sometimes this can irritate the lining of the lungs as well. But something else that sometimes arises from breathing in tropospheric ozone is high levels of tropospheric ozone are associated with an increased risk of respiratory infections, and I'm using that phrasing very carefully on purpose because this is one of those sort of correlation causation sort of things. Just because two variables are correlated doesn't mean that one variable causes the other. So high tropospheric ozone doesn't necessarily cause increased risk in respiratory infections. It's just that when you have a heightening in respiratory infections, there's also a similar increase in tropospheric ozone. But that is not to say that tropospheric ozone itself causes respiratory infections. There's just a tendency that as tropospheric ozone increases, the risk for respiratory infections also increases with it. And another thing about tropospheric ozone is this can actually lead to crop damage. This can lead to damage to plants if plants interact with high levels of tropospheric ozone. This leads to tissue damage in a lot of plants that are susceptible to high levels of O3, which is ozone. And another pollutant that we looked at is aerosols. Another pollutant that we introduced was aerosols. And a lot of times these are a byproduct of some sort of combustion reactions. And aerosols are most numerously produced by volcanic eruptions, but to some extent they're also produced by wildfires. And in a previous segment, we talked about the extent of the impacts of aerosols and what can happen if they what can happen if they manage to make their way into the stratosphere, where their impacts tend to be more long-lived versus when they're in the troposphere, where their impacts are more short-lived. But usually, like we just said, the highest concentrations usually originate from wildfires, and when you see smoke from a fire, typically the smoke that you see is those really fine particles of solid matter, those aerosols. And volcanoes release a lot more aerosols because they also, not only do they release smoke, but they also release a lot of ash into the atmosphere, and also volcanoes tend to generate more heat than wildfires, so those updrafts that are generated by volcanoes tend to reach a higher level of the atmosphere than, say, the smoke of a wildfire. Now, like I said, you can sort of, in a previous segment, sometimes the wildfire smoke can reach the stratosphere, but volcanic ash has a much higher chance of getting into the stratosphere than, say, an intense wildfire. And this is one of the reasons why firefighters wear their own artificial breathing apparatus, is because if you breathe in too many of these aerosols, then you can accumulate all this solid matter in your lungs, which can obstruct the lining of the lungs and therefore limit how much oxygen can reach your blood cells. So if the lining of your lungs is obstructed by aerosols, then you can't take in as much oxygen, or you can take in oxygen, but it won't be transferred to the blood cells, which means the oxygen levels of your body can be impacted if you breathe in too much aerosols. This is one of the reasons why smoke inhalation is such a big deal. If you happen to be in a burning building, God forbid, that's why you want to make sure you stay away from the smoke, because if you inhale too much smoke, then you get too much of that fine particulate matter accumulating in your lungs, and that limits the amount of oxygen that your body can keep inside of it. And this is something else that we kind of alluded to, but if you get a really intense, say, volcanic eruption producing very high concentrations of aerosols, this can result in a cooling effect, because a lot of aerosols are very efficient at reflecting solar radiation. So if your aerosols are reflecting solar radiation from the ground, that means the Earth is not going to be absorbing that solar radiation, which is going to result in a cooling effect. And in really intense volcanic eruptions, like say Krakatoa, for example, uh, arguably one of the most intense volcanic eruptions that this planet has ever seen, at least in the time that humans have inhabited it. Uh, those sort of intense eruptions can result in cooling effects that can last days to weeks to, in really extreme cases, sometimes even months. It just depends on how long it takes for the aerosols that make it into the stratosphere. It depends on how long it takes for those to sort of disperse and limit the cooling that occurs. And again, if your aerosols make it only into the troposphere, not the stratosphere, then the cooling effect is very short-lived because the tropospheric air is much more likely to sort of mix those aerosols out and reduce their concentrations in the process versus the stratosphere, which has very stable air. And thus, it's much harder to get those turbulent motions that mix out and lower the concentration of aerosols. And another one that we care about is carbon monoxide. And this one is kind of malicious in a way because there's really no way for the human body to detect carbon monoxide. It doesn't have any color, there's no odor, there's no taste, and this is just something that really is not something that we want to deal with. Usually, sometimes you won't even know that carbon monoxide is in the air until you start experiencing some of the symptoms from inhaling too much of it. But carbon monoxide is sometimes a byproduct of combustion, so that is some sort of process that involves burning. And if this takes place in an environment that is deficient in oxygen, this can result in the formation of carbon monoxide. And typically, a combustion reaction involves some sort of hydrocarbon that's on fire, and also there's oxygen involved. So, sort of like you can sort of think of the fire triangle if that helps you think about what's going on. So you mix oxygen, heat, and some sort of combustible, and when that burns, that gives off two gases. That gives off carbon dioxide and water. But if you've got an environment that is deficient in oxygen, sometimes instead of getting carbon dioxide, you get carbon monoxide, which has one less oxygen atom. Carbon dioxide can also be harmful if you inhale too much of it, but carbon monoxide is much more dangerous, even in lower concentrations than carbon dioxide is. And there's a lot of theories about why exactly carbon monoxide is so dangerous, but one of the running theories is that when carbon monoxide binds to the molecules of some living cells, it can actually shut down the cell's ability to carry oxygen. And of course, your body needs to circulate oxygen in order to maintain all of the bodily functions that occur. So if you inhale too much of this stuff, then those bodily functions can be inhibited. And symptoms of inhaling too much carbon monoxide include headache, sometimes a very intense headache, nausea, dizziness, weakness, and fatigue. Sometimes even people lose awareness of their surroundings to some extent if they start getting carbon monoxide poisoning. But that's one of the reasons why we care about this sort of atmospheric pollutant, because it can have a very detrimental effect on the health of human life. Another one that we care about, although for a slightly different reason, is sulfur dioxide. And this is also sometimes a byproduct of certain types of combustion that can occur. This can also result in damage to the respiratory system, but this also has a secondary effect that is much more related to the atmosphere. Actually two effects. One of which is sulfur dioxide can react with certain other constituents in the atmosphere that can lead to the formation of aerosols. Which again are those fine particulate solid matter, so solid particles that can reflect solar radiation. But probably the one of greater concern is if sulfur dioxide is released into the atmosphere and it happens to interact with, say, water vapor or liquid water, this can actually lead to the formation of acid rain, which more specifically, this can lead to the formation of sulfuric acid. So if you're interested in chemical reactions, that's the typical chemical reaction that occurs. So sulfur dioxide interacts with both H2O, which is water, and also with molecular oxygen, and that reaction can then result in the production of sulfuric acid, which is H2SO4. And any chemist will tell you that concentrated sulfuric acid is definitely not something you want to get on your skin. So that's one of the reasons why we like limiting sulfur dioxide, because if we limit sulfur dioxide, then we don't have to worry about acid rain. We don't have to worry about sulfuric acid raining down from the sky, which is definitely something that we don't want to be worrying about if we can avoid it. Another one, again, sort of a broad overview, nitrogen oxides, which is nitrogen bonded with any physically possible number of oxygen atoms. And typically, we kind of talked about this earlier, how usually this plays a key role in the formation of tropospheric ozone, and that is something that occurs in what's referred to as a photochemical reaction, where you have some sort of nitrogen oxide, so in this case nitrogen dioxide, and then if that reacts with a high energy photon, like say an ultraviolet ray of light, then that reaction can then result in the formation of nitrogen monoxide and then ozone, O3. So uh, this uh, this is something that you typically want to. This is why you want to limit the amount of nitrogen oxides that are emitted into the atmosphere, because again, if you also there should be an O2 on the left hand side of this reaction equation, but this photochemical reaction can lead to we call it a photochemical reaction because it requires a high energy photon to be part of the reactant. But again, nitrogen oxide, when it reacts with a high energy photon, it can result in the release of ozone, which if that occurs in the troposphere, that increases tropospheric ozone levels. And of course, we don't want high levels of tropospheric ozone. We want stratospheric ozone, but not tropospheric ozone. And also nitrogen oxides under the right conditions can also lead to the formation of acid rain, but usually the bigger concern is the formation of ozone. But this is also leading to the formation of acid rain, specifically nitric acid, is also within the realm of possibility. So again, if these nitrogen oxides, in this case nitrogen dioxide, interacts with the water, then you can lead to, this is actually two different acids. This is nitrous acid, which is also kind of dangerous, but it's not nearly as potent as this term on the right-hand side, which is nitric acid, which is a very strong acid and also something you don't want on your skin or anywhere near your skin for that matter. And then lastly, the one that we'll look at is chlorofluorocarbons. Again, we abbreviate that CFCs. We don't, as far as effects to human health, this isn't as big of a deal, but the long-term effects of these gases can be a severe threat to life on Earth. And the reason why is because these particular molecules can react with ultraviolet radiation, again, a photochemical reaction, which can produce chlorine. And if you produce high levels of chlorine where there's a lot of ozone, that can actually lead to the rapid destruction of ozone. In fact, it doesn't take very much in the way of chlorofluorocarbons to lead to the rapid destruction of a lot of ozone. This is one of the reasons why these were used as sort of refrigerants a long time ago, and then the ozone hole was discovered, and then there was some publications about how these molecules can be associated or attributed to the destruction of ozone. So there was a big campaign to eliminate these from our emissions, and in doing so, the ozone layer has gradually been restoring itself. But these actually can very rapidly destroy ozone, especially if they can find their way into the stratosphere. So these are if they find their way into the stratosphere, they destroy a lot of the stratospheric ozone. Then that allows a lot more solar radiation to reach ground level, which can have its own detrimental effects. So this can also, if you decrease the concentration of stratospheric ozone, you let in more ultraviolet radiation, and if that increase in ultraviolet radiation starts interacting with nitrogen oxides, then that can increase your concentrations of tropospheric ozone, which is bad ozone. We want stratospheric ozone, which is good. So not only do CFCs eliminate the good and increase the bad, that's basically what they do. They eliminate the good and increase the bad, and that's obviously not something that we want. And of course, if you have increased ultraviolet radiation levels, one of the reasons why sunscreen is such a big deal in the summer, because that's usually when ultraviolet radiation levels are highest, that increases the risk of cancerous mutations, and not just in humans, but too much ultraviolet radiation for plants can also be a bad thing. It can actually lead to cancerous mutations in plants. So plants need ultraviolet radiation to produce glucose, a process known as photosynthesis, and we'll actually talk a little bit more about that in the next lecture. But too much ultraviolet radiation is not good for plant life. It sort of goes with that saying, too much of anything isn't necessarily a good thing, or it can be a bad thing, or too much of a good thing can be a bad thing, however that goes. But CFCs can reduce stratospheric ozone, which can then increase ultraviolet radiation in the troposphere, which can have its own set of harmful health effects, but can also just lead to higher concentrations of tropospheric ozone, which we don't like. We like stratospheric ozone, but not tropospheric ozone. So that's going to do it for this final segment on lecture 25. And so that's going to do it for lecture 25. So with that, I will see you all in the next lecture where we will continue to discuss the role of chemistry in the atmosphere. So I will see you all there.